basically what these different ideas are saying, these different theorems, is that we can go through and think about the limit of each piece as a little bite-sized chunk and then add it up. Another way to think about it, or another way to say it, is that we can also think about what we call direct substitution as being how we figure out the limit. It doesn't always work, but when it works, it's a pretty quick way to find it. So we're going to use all this, come down here, and we're going to go through a problem together. Notice that it's set up kind of like a proof, right? On the left is where we're going to put our work, and on the right we're going to put the justification. Here is the good news. I don't have anything like this on the quiz, on the exam, anywhere else. So let's just practice using it, but I'm not going to test you on names of all the theorems and ideas here. Okay, first of all, do we see how we've got a limit and there are 3 different little pieces there? Do we see the pieces? Okay, I'm going to pick some colors and I'm going to make sure I can kind of show you where everything's going. So I'm going to make this one kind of that peachy color, just so we can differentiate these 3 terms a little bit more as I break them apart. Okay. Let me zoom in just a little. Ooh. I know. I actually picked this color first, but I decided that I did not want that.
Wait. Oh, I have the exact same colors.
Ooh.
Oh.
The same pack and everything. That's perfect. Okay. So I'm going to start by pulling this apart into little bite-sized pieces. So think about this and, oh, that's a -2. Think about this and you are trying to give something to a little kid to eat and you're just pulling this apart into little bite-sized pieces. So the first thing I'm going to do is pull apart into 3 limits, all approaching -2, and I'm taking each term independently. So notice that this is that first term and the second and the third. So I kind of use 2 properties here. Actually, we added every time. So I only used 1, but this would be the limit of a sum would be my justification, is that I can pull them apart and I can find the limit of each individually and then add them together. So that's something we're allowed to do, is break it apart that much. I was going to say it was sum or difference, but we didn't have any that were subtraction. Well, I guess we could think of this as being subtraction because it was a negative. So sum and difference. We'll say both. That was a -3x. Moving to the next one. One of the other ideas that was up there said that if you were multiplying by a constant, do we agree 6 is a constant number? Right? 6 is 6 all day long. So we can take that 6 and we can move it out front and we can find the limit as x approaches -2 of just x squared. So one of our rules said that if we had a constant, we could pull that out front. Same thing with this one. I can pull my -3 out front as a constant, and then I can take the limit as x approaches -2 of x. And then do you see how the last one doesn't even have a variable? Like it's just 1. So I'm going to leave that as it is. It doesn't have the same situation as the other 2 that we just looked at. So this one was limit of a constant multiple is what I used to pull those out front. Limit of a constant multiple. Does it almost remind you a little bit of logarithms when we were pulling apart with those rules as well, like expanding and condensing? That's what it makes me think of too. So now we're actually going to go through and find our answer. So there are times when what we call direct substitution works. Direct substitution is exactly what it sounds like. You are going to take the number you're looking for the limit of and you are going to sub it right in. So if I plug in -2, what is -2 squared? 4. 4 times 6? 24. So this first value gives me 24. Go to this one. Again, we can sub right in with direct substitution. There are times we can't. We're going to talk about those in a minute, right? It can't always be this easy. It'd be nice, but it can't. If I plug in -2, it's going to be -2. If I multiply it by the -3 out front, it's going to be 6. And then, do I have a spot that I can plug in the -2? No. So the limit is just going to be 1 because this is going to stay a constant 1 the whole time, no matter where I am on my graph. So picture that graph for a minute. If you have a graph at 1, it's always going to be at 1. Agreed? Like it's not going to go anywhere else. It's always at 1. So even if I'm at -2, I'm still going to be at 1 in terms of my y. And then what do I get when I add those numbers together? 31. So if you were to go to the graph, like we did in section 13.1, and you were to get closer and closer and closer to -2 on either side, you should find that your answer is 31. Okay, so that's what it's going to approach. Again, remember the limits are an approach thing. Okay, flip to the next page when you're ready. So this is what we call direct substitution, and we actually give it that name on the next page. So we can find limits by direct substitution. Again, that means actually just plugging it in. And no, I'm not going to make you break it apart into pieces every single time. We just did that once to see how it all works. Okay, I feel like once is good enough for us on that one. So let's directly substitute in the 2. So if I substitute it in, 2 squared is 4, plus 2 times 6 is 12. All over, let's sub in the 2 again, 2 to the 4th power, 16 plus 3. So in the numerator, I have 16. In the denominator, I have 19. I can't reduce that. This would be my limit. So again, if you went to the graph, on your graph, and you started getting real close to 2, 1.9, 1.99, 1.999, and then if you went the other way, right, 2.1, 2.01, 2.001, you should find that you're getting closer and closer to this number, or the decimal equivalent of that number. Isn't that nice and easy? That's just substitution, right? That's like something we learned back in, I don't know, probably even like a pre-algebra sort of day. So, we can't always do that though. This is the bummer. So, each problem is a little different about why you can't use direct substitution. This one would have been fine. None of the rest are though. So take a look at part B, and let's pretend we wanted to use direct substitution again because, well, it's easy, right? If I try to plug in 4, what's going to happen? 0 in the denominator. So I can't use direct substitution because the denominator would equal 0. And that's bad news there. Could I apply the quotient rule from the previous page? Still no, because I would still have to divide by something that's 0. So the answer to that would be no again, because I would still have to divide by 0. So this is where we come into strategies. We're going to get 3 strategies total of different ways that we can do these problems and make them doable so we can actually use substitution. So we're still going to be able to do it, but we have to do some legwork first. Strategy number 1. And I'm going to write these down because these are the same 3 strategies you're going to see in the homework, on the quiz, on the test. You know how sometimes when you get the notes and you feel like, oh, they didn't match the homework or they didn't match stuff down the road? Like there are 3 strategies: notes, homework, quiz. Okay? So the first strategy is going to be to factor and simplify. So sometimes that is going to help us. And I will show you how. Strategy number 1, factor and simplify. All right, can I factor the numerator? Is there anything I can do to x minus 4? No. Okay. What about the denominator? What can it factor into? Looks like a difference of squares. What is it? X plus 4, x minus 4. And we're going to still write our limit out front because we're still looking for the limit. Okay, so as we're simplifying, what can cancel? The x minus 4s. So the limit as x approaches 4 of 1 over x plus 4. This is a game of like, how about now? Have you seen that one? I can't think of his name. He's so funny. He's a comedian. And he's like, I try to send a file, and it says the file is too big. So my response is always to try to send it again. And he's like, how silly am I to try to send it again? I'm basically asking the computer, like, you wouldn't let me a minute ago, how about now? That's actually the game we're playing, though, is we're playing the how about now game. So a minute ago, could I plug in 4? No. How about now? Now I can. So now let's actually plug in the 4. If I plug in the 4, what do I get for my limit? 1 over 8. So in a way, I'm still kind of using my direct substitution, but before I can do it, I have to get to a point where it can actually be used. All right, look at part C. Can I plug in 0? No. But again, we're going to have one of those how about now moments. So we're going to mess with it a little bit, and then we're going to see if we can plug it in. So our strategy for this one is going to be to multiply out and then simplify. So sometimes you have to kind of make it bigger and a little bit worse before it gets better. So multiply it out and then try to simplify it. So what is the only thing I can multiply out in the top? 4 plus h. So let's go ahead and multiply that out. Can't do anything with the minus 16, can't do anything with the h. Limit is still as h approaches 0. So remember, we've got 2 sets of these parentheses. We've got a 4 plus h times a 4 plus h. All right, 4 times 4.
16.
16. 4h and another 4h. 8h's total. And then h times h. H squared. Okay. Let's keep going. What can I simplify in that numerator? The 16s go away. So now I have my limit as h approaches 0 of h squared plus 8h all over h. Okay, so let's play the how about now game. Can I plug it in now? No. Still no. So in the top, let's go back to our first method of factoring. Is there something I could factor out of the numerator? H. So let's rewrite it. The limit as h approaches 0. I'm going to pull out an h. What can I cancel? The h's can cancel. So now I have the limit as h approaches 0 of h plus 8. How about now? Can I plug in 0 now? Yep. And my answer is 8. And if you did this on your graph, just like we were doing in 13.1, you would get the same answer, right? So if you went in from both directions to look at where it's headed in terms of y, it's headed toward 8. All right, last one. Ooh, there are only 3 today, I think. Did I have any more? This might be it for today. That's kind of short for us. Oh, I love that. Yeah, because we're not going to do the absolute values. Okay, we don't get quite that far. So we're going to come down here, though. We've got one more. So could I plug in my 1? No. Do you remember back in, I'm going to go August. or early September. We talked about rationalizing the denominator, and I said later in the year, you're gonna maybe need to rationalize the numerator. We have reached later in the year. So our strategy that we sometimes need is to rationalize the numerator. We have finally reached that day, like 8 months later, but here we are. So our other strategy, our third strategy of the bunch, is to rationalize the numerator to help us find the limit. All right, here we go. Limit as x approaches 1. In the numerator, we have the square root of x minus 1 over x minus 1. How can I get rid of the root in the numerator? What would I multiply by? Square root, yes. So we multiply by the conjugate, which is a fancy way of saying same z's, but change your sign, right? So again, we call this the conjugate, same z's, but change the sign is the way I refer to it. If I multiply it to the top, I also have to multiply it to the bottom. That's been a rule we've had in math for a long time. All right, here we go. Let's multiply it out. This is another situation where it's going to get a little bit worse before it gets a little bit better, unfortunately. Let's start by multiplying out the top. And actually, I'm going to leave the denominator alone. Typically, when we multiply stuff to the denominator, it's better not to multiply it out. But that's also a situation you could feel out, right? Like you could leave it unmultiplied and see where we go. And then if it doesn't help you, you could multiply it. So let's deal with the top. Root x times root x is what? X, right? Because it's the square root of x squared. Okay? Root x times 1 is, and then this is going to give me a negative root x, so what happens to that middle term? Gone. Negative 1 times positive 1, minus 1. Ooh, interesting. Can I kind of use strategy number 1 again? What can I do? Cancel it, right? Okay, so the limit as x approaches 1 of 1 all over root x plus 1. So play the how about now game. Can I plug it in now? Yes or no? Yes. What do we know the square root of 1 is? 1. So I have 1 over 1 plus 1, which is 1/2. Or you could put 0.5. It doesn't matter. This isn't a section where it has to be a fraction or it has to be a decimal. I'm okay with either. Okay? So we're going to use the strategies to help us so that we can use direct substitution. That is the goal for today. Are you ready? Can we do this? We are okay? Okay. All right. Homework is, I'm going to call this assignment number 2 because I kind of grouped the last 2 together. Assignment number 2, page 855, numbers 5 to 7 and 11 to 18. They're not going to